solutions. Okay, this is number 3 on the 4D FIP. Your turn to drag the family crate around behind you. I don't know who writes this junk. So we have this crate being dragged around the front yard. We have a normal force. We have a force of gravity. We have a force of static friction. And the rope that you're using to pull the whole mess is angled at 40 degrees above the horizontal. And we've got Fg equals mg. So what we know is that mu s, it's a terrible mu, mu s is 0.149. Obviously this is snowy or icy ground because we wouldn't have that low a coefficient of friction on grass or mud. How much force do you need to get? Oh, and the mass is 56.0 kg. So we have, again, our 3 pieces of information. This is the one where I started down one path and realized the algebra was going to be really hideous, and I took the other route. So you can totally do that. So sum of forces on the y is equal to 0. It's equal to, we have 3 forces on the y-axis, Fn, Fg, and F applied on the y. So we generally know that we have to create an expression for Fn because we're using that mu k. So I'm going to go ahead and assume that, even though it could be a blind alley. Let's see. How did I do this on this one? So negative Fg minus F applied. And since I'm looking at the y component of the applied force, that's going to be times sine of theta. So I've got my expression for Fn set up and set aside. And this is then where I started to look to the x-axis, thinking I would sub in there. So sum of forces, not sub of forces, is equal to 0 because it hasn't started to move yet. And until it starts to move, applied force on the x is going to be equal to static friction. So what I have, of course, is just the 2 forces, force of static friction and force applied on the x. So force of static friction is equal to the applied force times cosine theta. And of course, applied force is what we're after. Oh gosh, yeah, I'm sorry. Woohoo. Let me move this to make room for the negative sign. Yeah, thank you, I forgot that. So they're equal and opposite. So I assumed then that I could go and do mu k equals mu s. Geez Louise. Mu s equals fs over fn. Mu s fn equals fs. And I went to plug all of this into here, and what I ended up with was applied force on 2 sides of the equation. And I looked at it and went, I don't have it in me today. I get there too. I get there too. So instead of instead of doing normal force into here and then this into here, I opted for another route. And you know what? You could do that, and it's just some ugly algebra. But I was feeling it yesterday. I couldn't do it. So what I did instead was I put, well, no, wait, that isn't any prettier, is it? Yeah, okay. Somehow it seemed like it to me. You know what, it's probably 6 1/2 dozen the other, but it seemed easier to me in the moment. And darn it, that's valid. Let me shrink that. So what I did was I plugged this into here, into this. So I have mu s times negative, and of course this is mg minus force applied sine theta equals negative F applied cosine theta, because I took this and subbed it in for that. And then it was just a matter of distributing the mu s. So we have negative mg mu s minus mu s, or mu, yeah, F applied sine theta equals negative F applied cosine theta. So now it's not too terrible. And it's honestly the big mental saver for me. You know what? It's the same darn thing. It's identical. Oh, wow. I see why it didn't look identical to me at the time. So, negative mass gravity mu s equals negative F applied cosine theta now plus mu s F applied sine theta. Mu s. I'm going to factor out my F applied. So that times negative of cosine, let's see, where did I lose? I lost something somewhere. No, I lost something else, but that's okay. Plus mu s sine theta. So now I can divide both sides by this expression, and I have the solution for F applied. Cut. So that gives me the solution for F applied. And what I get as a raw answer is 94.978, etc. So we get 95 newtons as the force that's needed. You okay?
Yeah, I must have did some calculator thing wrong because I have everything.
You have everything there. Okay. And that's the other thing. And I mean, how many of you in doing all these problems have had that happen? We're like, I entered it all, and you know, I have the exact same algebra, and I have a calculator. I've done it too. So the biggest thing I can tell you with these, and while I absolutely will never ever tell you, like, solve for each piece, I'm not telling you that. Create the algebraic expression, but it doesn't hurt to make notes off to yourself of what all the pieces equal so that you can compare those values. Yeah? Ready to go to the next one? Sledding down the hill in Rogers. Oh, I see what's happening. That's not good. Yes. Okay. So we've got sledding on this 11.5 degree slope. We have F of G, we have Fn, and we have F of kinetic friction because you are going down. A number of people seem to want to put in an applied force here, and anytime that you're thinking about a slope situation where something is sliding down a slope, what I want you to imagine as your sort of like mental touchstone is yourself on a sled on a hill. Do you need somebody, if you're in the middle of the hill, do you need to be pushed? No. That's what you need to think about in those situations, and then you don't put in an applied force. The force of gravity will more than get you down the hill, and the force of kinetic friction on a nice well-packed sled hill has never stopped me. You know, and you still go sailing. So, all right. We start off, of course, well, what we have, the only piece of information we have is mu k. We have mu k is equal to 0.095, and let me tell you, that is like sledding on ice. That is a really low coefficient of friction. This is some good sledding. So on the y, of course, it's 0. We've got Fn plus Fgy. So Fn equals negative Fgy. And if you really want to be anal about it, you probably should, you take this all the way down to, well, that means it equals negative Fg cosine theta. Well, that means that Fn equals negative mg cosine theta. And you have just proved that Fn equals negative mg cosine theta. Okay. We also have, of course, oops, I don't know why that happened. We have mu k equals Fk over Fn, therefore mu k Fn equals Fk. We can go ahead and do our, so that would give us mu k times negative mg cosine theta is equal to Fk. Well, that comes in handy because the next thing we're going to do is sum of forces on the x-axis. We know this is equal to ma, and a is what we're looking for. We want the magnitude of your acceleration. And we know that that's going to equal mass, well, let's back up. That's going to equal Fgx, which is negative. It's Cartesian negative and it's downhill, so that works out, plus Fk, which is a positive. So Ma equals, and we know that the Fgx is mass, gravity, sine theta. And we know that Fk, we have an expression for over here, is equal to mu k is equal to mu k times negative mg cosine theta. A few people got really concerned about the fact that mass was not given in this problem. When you see a problem like this and mass is not given, you have to kind of trust the algebra. Get these down to the point where you've got expressions that all have mass, and guess what? It all cancels out. So, and this is that same thing we were talking about with the water slide, you know. And I see this algebraically. I get it algebraically. I believe in algebra, that the algebra says that your mass does not matter in terms of your acceleration. I also know that me and the little 100-pound moms go down the slide with their toddlers at very different rates of acceleration. I know the algebra, I know my experience. So it's one of those places where they don't seem to match. So we have acceleration is equal to gravity times sine theta plus mu k times negative g times cosine theta. And if we look back at these, this one is going to be a negative, this one is going to be a positive, which a negative g will give us a positive number. So that works. And the acceleration that you get is negative 1.04 on and on and on. With 2 sig figs, that's 1.0 meters per second squared, which is a respectable rate of acceleration on a hill when it's just you and the hill and no helmet. Questions, comments, concerns?